Hello, my name is Zibo Jiang. I am from Xi'an Jiaotong University and Innovia Materials in Shanghai, China. I am going to present the effects of composition segregation and alternative current pooling in PMN-PT crystals on ultrasound transducer performance. The main points of this talk include the following 4 points. First, we will clarify the effects of composition segregation on ultrasound transducer performances. We will discuss the effects of AC pooling and medium temperature pooling on ultrasound transducer performances. And then we will discuss the configuration of electrically parallel stacking of PMN-PT crystals in improving ultrasound transducer signal strength. Lastly, we'll discuss how the above results can expand the usable proportion of relaxer crystals. Here are some background information. What are the technical barriers for PMN-PT and PIM PMN-PT crystal applications? The picture on the left shows the composition segregation during VGF or Bridgman growth can lead to property segregation, including variation in free relative permittivity and piezoelectric constants. The consensus is yet to be established on the acceptable PT composition for industrial applications. Currently, 29% of PT to 31% of PT within the morphotropic phase boundary are being used by industrial leaders. For the high power application, as indicated in the picture on the lower left, shows there is just not enough output signal strength due to lower coercive field coming out of crystals, as the coercive field of the crystal is only 1/3 to half of the applications for those power applications. Another important background to this research is the recent study on AC pooling under elevated temperature on PMN-PT crystals. That shows that after AC pooling, the domain structures observed under PFM shows the increase in domain wall density, which indicates the enhancements in piezoelectric properties are permanent. And secondly, AC pooling with optimized frequency and field cooling temperature up to 200 degrees can increase free relative permittivity and piezoelectric coefficient up to 50%. The picture on the lower left shows that schematic images of 4 pooling conditions, all of them with field cooling, and that crystals of lower PT content have the potential to be qualified for industrial application with AC pooling and elevated temperature pooling. Here is the composition segregation's effect on materials properties. The table on the left shows the key materials properties for PMM 29% of PT to PMM 31% of PT with 5 composition in the intervals. Firstly, throughout the usable length of the ingot, the speed of sound, acoustic impedance change monotonically with composition. Secondly, free relative permittivity and piezoelectric constant D33 change substantially with composition. Thirdly, relative permittivity at 8 MHz and electromechanical coupling coefficient KT do not change much with composition. And the above measurements are in line with the previous studies. Here is the method of transducer fabrication and evaluation for different PMN-PT compositions. The diagram on the upper left shows that the photograph of the fabricated transducers with 10 MHz in application, and each transducer is composed of a crystal layer of 2.5 by 2.5 by 0.2 millimeters in size, a backing layer, no matching layer, and all potted in a case made of brass. Secondly, the performance of transducers, such as impedance versus frequency profiles, time and frequency domain response amplitudes, were first simulated by piezo CAD software, and then we will measure the real transducer performance, use pulse cycle test. Subsequently, center frequency, bandwidth, and two-way insertion loss were measured. And here are some transducer simulation results. The table on the left shows the piezo-CAD simulation results for PMN-PT crystals. The coefficient variation of electromechanical coupling coefficient is less than 3%. That of the center frequency is 2.4%, and that of minus 6 dB bandwidth is 6.4%. The only property which clearly improves with the increased PT content is minus 6 dB bandwidth. The static piezoelectric properties such as free relative permittivity and piezoelectric constant D33 do not cause the key transducer performance parameters such as center frequency and bandwidth to vary to the same degree. There are some real transducer testing results. The table on the left shows the measured crystal transducer performances for the various PT contents. Firstly, the coefficient variation of center frequency for different PT content is found to be only 1.4%. Secondly, the increase in PT concentration leads to mild and consistent increase in transducer bandwidths. And thirdly, the variation in real transducer performances are much smaller in piezoelectric or dielectric properties, aligned with the simulation results and well within the device design tolerances. And fourthly, the improved static piezoelectric properties have limited impact on key transducer properties, whereas the elastic compliance properties play key roles. And here is another experiment method for AC polling and medium temperature polling. The picture on the upper left are 4 sets of polling conditions. Firstly, we take PMN-PT or 27% of PT crystals and compare key properties with the crystals of other PT concentrations from the same ingot. And secondly, we pour the 27% of PT crystals with 4 different conditions. A, pouring at 25 degrees and 410 volts per millimeter for 10 seconds. B, pouring at 65 degrees Celsius and 205 volts per millimeter for 10 seconds, half of the previous condition. C, pouring at 25 degrees under AC field of square wave 410 volts per millimeter with 0.1 Hertz applied for 3 cycles. D, polling at 65 degrees C under AC field of square wave 205 volts per millimeter and 0.1 Hertz applied for 3 cycles. Lastly, we will use the pore crystal to make single element transducer of 200 kHz with a backing layer and a matching layer and testing water for pulse cycle response. The setup is on the lower left. Here are the effects of AC polling conditions on materials properties. The 2 images on the left shows the phase transition temperature, and hysteresis loop confirms that 65 degrees Celsius is ideal for ease of AC polling and transducer rework process. The table on the lower left shows the crystal materials properties of 1.7 millimeter thick crystals under room temperature and 24 hours after different polling conditions. With ACP, the relative free permittivity value sees 19% of increase under 25 degrees and 16% of increase under 65 degrees. The D33 value sees 13% of increase under 25 degrees and 24% of increase under 65 degrees. The electromechanical coupling coefficient sees 60% of increase under both 25 and 65 degrees. Overall, ACP under 65 degrees C gives rise to better piezoelectric properties. This might be attributed to the ease of domain wall movements. Here are the effects of AC pooling condition on transducer performances. The table on the left shows the comparison of bandwidth center frequency receive a free field voltage response among PMN-PT transducers of different pooling and stacking conditions. Firstly, the single layer transducer with 65 degrees Celsius AC pooling has on average a bandwidth of 6.4% higher than the one with 25 degrees Celsius DCP. And the stacked transducer with 65 ACP has on average a bandwidth of 2.6% higher than those with 25 degrees Celsius DCP. Secondly, under different pooling conditions, the center frequencies of the transducers is more related to the elastic compliance properties rather than the static piezoelectric properties. And thirdly, this conclusion is consistent with our conclusion on transducers with different PMN-PT compositions. And here are the effects of electrically parallel stacking configuration on transducer properties. The picture on the upper left shows the single layer versus stacked PMN-PT crystal transducer for 200 kHz transducer. By stacking two layers of the same crystal of opposite pooling directions, one can obtain the same center frequency as that of the single layer with a total thickness of the two layers. The picture on the lower left shows the time domain receiver voltage spectrum for transducer of different pooling and stacking conditions. We can conclude that while the bandwidth performances are similar, the signal strength can be significantly improved by stacking two crystals together. For DCP transducers, stacked configuration sees an increase of 190% in M0, a key indicator of signal strength. Whereas for ACP, the stacked transducers sees an increase of 162% in M0. The stacked transducers could respond to exciting signal much better due to the increased capacitance. Here are the conclusions. The effects of PMN-PT composition segregation were studied on 10 MHz transducer performances by piezo-CAT and real transducer pulse cycle tests. From 29% of PT to 31% of PT, the PMN-PT transducer bandwidth sees a mild increase, but the other transducer properties are relatively stable, suggesting that elastic compliance properties of the piezoelectric materials play key roles. For PMN-PT, 27% of PT crystals, AC pooling under either 25 degrees Celsius or 65 degrees Celsius could increase materials properties to the level of PMN-PT 29% of PT, extending the usable ingot and reducing the cost of the overall crystal usage. AC pooling mildly increases bandwidth of 200 kHz transducers, particularly under 65 degrees Celsius, due to an increase in domain wall density. The stacked transducer could respond to exciting signal much better due to the increased capacitance, almost tripling in transducer output strength for 200 kHz applications. Lastly, I would like to thank Professor Yezuo Guang of Simon Fraser University for in-depth discussion, and special thanks for Innovia Materials for sponsoring the research and providing the material support.